Okay, so this one is going to be about work, energy, and to understand what's going on. So the first concept I'm going to talk about is work. And work can be many things. Work is F dot D, okay, which is a vector, what's called a dot product. But we use it more commonly. We're used to this F. Okay, your units for work are newtons times meters, which is a joule. So if I asked you to find how much work is done as the box moves 5 meters, okay? But we're going to move 5 meters this way. So if I put this here, if I draw them tail to tail, this is my distance, this is my force, this is the angle between the two. And let's just make this up. Let's say this is 20 degrees. Okay? So the work done by this force is FD times the cosine of the angle. So it's the force times the distance times the cosine of 20 degrees. And that is 47 joules. Okay, that's how much work is done. That's the simplest way to do work. And so if we get that opportunity, that's what I'm going to do. But we don't always get that opportunity. We also find that work is equal to the integral of F with respect to position. Okay, and where do we use this? Well, we use this in a couple of things. Like maybe they might give me a force equation. They may say that force is equal to 3x squared plus 2, and they might say what work is done from 0 to 2 meters. Okay, so here's my equation that I'm going to use. So work is equal to the integral of 3x squared plus 2x from 0 to 2. So now be careful, don't do this with time, because work is not the integral of force with respect to time. That's different. But this is force with respect to position. So I get 3x to the third over 3 plus 2x squared over 2, evaluated from 0 to 2, which the 3's are going to cancel, the 2's are going to cancel. So I'm going to get 2 to the third plus 2 squared, and then minus, of course, these are 0 to the third plus 0 squared. So I get 8 plus 4, which is 12 joules. Okay, so that's one way to do work. That's another way to do work. Okay, another way we have to look at this is, since work is the integral of force with respect to position, it's the area under a force distance graph. So if I have something like that, you're going to have area under here. So that looks a lot like a Riemann sum, but that's essentially what we're doing. Okay, so there's my area under the curve, and that would be my work. So if I happen to have a force position graph, that's what I'm going to have. And I've got one more thing that work equals. And work net is equal to change in kinetic energy. Okay, and kinetic energy that's the energy of something in motion. So kinetic energy is 1/2 mv squared. And that is kinetic energy. So since work is the change in kinetic energy, it is 1/2 mv final squared minus 1/2 mv naught squared. And that's another way that you can look at work. So say for instance, I'm told that a car is going 10 meters per second when friction acts, so we're sliding to a stop here, and the final velocity is 5 meters per second. How much work is done by the force or by friction if the mass of the car is, let's give it 1,000 kilogram mass. Okay, so work is equal to delta K. Now no, this is net work, so if there were other forces acting, it would be the work of all those forces added together. So 1/2 mv final squared minus 1/2 mv naught squared. So I'm going to do 1/2 times the mass times the velocity final, which is 5, minus the 1/2 m times the velocity initial, which is 10. Oh, I didn't plug my m in. My m is 1,000. Let's cross that out. Okay, so alright, I get negative 37,500 joules. And so that means the negative, work is a scalar. So the negative means it takes or it steals that much energy. Okay, if we do positive work, we give energy. If we do negative work, we take away energy. All right, the next type of energy is gravitational potential energy. And gravitational potential energy is UG. And UG equals mgh. So mass times the acceleration due to gravity times the height. So if I have a tree and I have a little squirrel up in the tree, and let's say the mass of the squirrel is, let's say we'll make the squirrel 2 kilograms, and let's say that he is 3 meters up in the tree, then the potential energy of the squirrel is the mass times the acceleration due to gravity times the height, which is 3 meters. So 13.6 times 3. So that is 58.8 joules. Now, there is this thing called the conservation of energy. Now, energy is always conserved. It doesn't matter in what situation, it's conserved within the universe. Okay, but in a certain system, it can be lost to something else. But if only conservative forces act, and friction and air resistance are non-conservative forces, but gravity is a conservative force. Then mechanical energy, which is K plus U, is conserved. So that means K naught plus U naught equals K final plus U final. And I like to use this anytime I see anything going from up high to down low or vice versa. I like to use this because it's a very straightforward thing to use. It works in just about every situation. So if I can use it, I'm going to cabbage onto energy, and that's what I'm going to use. So for our squirrel, how fast will the squirrel hit the ground? Okay, so this squirrel's up in the tree and we want to know how fast he's going to hit the ground. So we're going to say, okay, well, his K naught in the beginning is 0 because his velocity is 0. His U naught is 58.8 joules. His U final is 0 because he's on the ground. So this is what I'm looking for. So 58.8 is equal to 1/2 m V final squared. So 58.8 is equal to 1/2 times the squirrel's mass of 2 times the velocity final squared. 1/2 times 2 is 1, so I get V final squared. I take the square root. V final is going to be 7.7 meters per second. And that is how we can use the conservation of energy. Okay. Now let's talk about power, and then we'll conclude this one, and then I'll come back again and I'll do springs because I didn't cover elastic potential energy, but I'll do that in another video. Power. Power is the rate Okay, sorry, I had to pause there for a moment. So power is work over time. That's our average power. The units are joules per second, which is called a watt. So that's a way that we can find the average power. So if 25 joules of work is done in 2 seconds, then the average power will be that 25 joules divided by 2 seconds, or 12.5 watts. Instantaneous power it can be one of two things. It can be derivative of work with respect to time. Again, I don't think we're going to see this one too much, but again, if I had I could take a derivative of a work function, or it could be the slope of a work time graph. So if I had the work time graph, it would be the slope. Not a very common thing that we see. It also can be F dot V. This is the one I think you'll see more often, and that's F V cosine of the angle between them, where F is force, V is velocity. So this is a pretty common thing that you might see on the AP test, as power is force dot the product, or the scalar product of force and velocity.